So, robotic telescopes. Well, in 2005, we bought these two big robotic telescopes because we wanted to build a global telescope network of optical telescopes. So we had the opportunity to buy two big ones, two 2-meter class telescopes. At the time, these telescopes were using almost entirely Java, from an operating system that was Java-based, to a scheduling system that was Java-based, to even a web control system that was a weird Java-based thing. And if any of you have ever used that sort of thing, then you'll know that it really was weird. But so that sort of sprung us forward in the world of telescopes. We had two, and two doesn't make a network though, really, does it? Particularly if people say we have a network of telescopes, but they're two separate telescopes operating totally independently. So anyway, we set ourselves the ideal of making more telescopes, so we did. We made 1-meter class telescopes, and we currently have 9 of these operating in the field, and one which is this one, which is our testing facility in our Santa Barbara headquarters. And we're also building these little 40-centimeter telescopes. Now, we built the 1 meters from the ground up, totally designed the electrical, mechanical, optical paths, and with the 40 centimeters, we built everything except the tube. We bought the tube. I thought somebody at the back then was just going, "Oh my God," but she was yawning. Whenever I give a public talk, I usually say these are about the size of R2-D2, but you're too sophisticated to need that sort of. We tend to put them in groups, so we have various sites across the world. So here's our siding spring installation with a 2-meter and 2 little 1 meters. They look so cute, don't they? And our Ceratololo installation in Chile with 3 of the 1 meters. So this is where our telescopes are spread out all across the world. We have 12 currently operating in each of these filled circles. Throughout this year and next year, we're going to be adding another 8 telescopes to that network. Predominantly, we're operating with 1-meter class telescopes. But the ideal was to make us able to respond very, very rapidly to things. So we could have lots and lots of observers, each putting their observations into a queue-based system, which would be able to rapidly respond to anything that was happening, TOO type events, so supernovae, time-varying things like exoplanets, asteroids, and that sort of thing. So when you speak to people and you say you say you're an astronomer, they've envisioned that you're something like this, that you go to an observatory site and you look through a telescope. Or maybe they see you more like this, as some sort of rock star that lives up a mountain. But actually, in reality, we're more like this. And I chose this picture because this is on the IAU website for careers in astronomy. That is look at that. That is a Sun Spark Station 5. Look at it. Yes, state of the art there, using Gaia. So we want to just be sitting at our desks and data comes in. We don't want to travel to exotic places and operate things that cost tens of billions of dollars when you're incredibly jet lagged. You want to be able to respond very, very quickly to things. And so that was what we wanted to do. We have all these telescopes. How do you make them work? Well, you have something beautiful like this, and there will be a test on this later. You start off with the world, and you start off with, which is people, and then you end up with instruments and telescopes, and then there's a whole load of stuff in the middle. But actually what that really boils down to is you need a black box. You need an astronomer sitting at their desk, and they just send things to the black box, and it just gets done. Okay? By the way, does anyone recognize this? That is the internet, if any of you are IT crowd fans. Okay. So we wanted to make it that we have a network, a true network. We also had a black box. We also wanted to make it as easy as possible for people to get their observations into the queue. So obviously, we had free reign. We were building a lot of this from the ground up. So we decided to go with Python. We could have carried on with Java, but Python seemed to be a much more friendly language to use. So this is what we developed, a Python package called LCOGT Pond, which was our schedule. You define blocks, you define molecules, which are like observations, and you define things to do with filters and exposure times, and pointings, where you want the telescope to point. And then you have your script. You put in a start time, an end time, an observatory, where you're going to point, and stuff about your particular observation, and you just send it. My block, dot save, bracket, bracket, done. Off it goes. But we have more than 1,000 active users, and so if you just let all of them do that, you end up with this, because they all want to observe the same thing at the same time at the same telescope. You also end up with this sometimes. You know, it's sometimes, even at the best observatory sites in the world, it sometimes snows, which really puts a dampener on things. So you don't want to have people who are just sending requests to a particular telescope for a particular time, because then they'll have to redo their job continuously. So I was trying to think of a way to visualize the problem that we have. We have a computer, an algorithm called the Robotic Autonomous Scheduler, and it takes all of these inputs from people and all of the different requirements in very vague abstracted terms, like, well, I have this particular target that I want to observe in the next week. That's it. You know, maybe you'll put some filters and exposure times because you're nice to us. It's really like that. You don't say where you want it to observe. You don't say particular time that you want it to observe. So our scheduler takes all of these inputs from these 1,000 people and fits them all together in a very, very efficient way, farming things out to different telescopes, adapting continuously when these telescopes aren't available for a variety of reasons, and avoiding all these clashes based on the weighting of different projects and whether you're going to have the opportunity to observe things again. So I have this very sophisticated graphic. It's like a very large multi-dimensional game of Tetris, and the Robotic Autonomous Scheduler is fitting your differently shaped observation requests together so that you end up with, I should have had these lines disappearing, but so that it fits together really, really nicely. I often call this robot the cyber controller, but it's like an autonomous brain that sits in our headquarters. And that's great because you don't then have to think, I need to use that telescope, you know, what's the visibility of my target there? Do I have to try and work out, you know, a variety of different parameters about that, and I've spent all day doing that and now this is closed. You just put it into the queue and it happens automatically. And that's the big difference, I think, with Las Cumbres and many other robotic telescope networks, is that we have this centralized cyber controller which takes all of these, that was a reference to Doctor Who, by the way, that takes all of these requests from all these over 1,000 different users and fits them all together and tries again, it tries its hardest to fit all these together and make them happen. The schedule at any one time will look 2 weeks into the future. That's the horizon. So it will churn out a schedule, a calendar of things to do on the entire network for 2 weeks. It takes around between 10,000 and 100,000 individual requests and fits them all together every 10 minutes, which is quite a serious undertaking. So I thought I'd show you the process and indicate what is doing the heavy lifting. So we have an observation submission interface, a web page or an API. So I showed you a Python library. We have an API and a Python library and a web page that you can submit your observation requests, and that's Python. We have an internal request handling and storage system, so that takes what the users send us and it packages them up into something which our cyber controller can weight against each other. So that's handled in Python. And then there's the schedule optimizer, and that's a commercial thing by Gurobi, and that does some very serious maths on this, on these abstracted requests. And then that thing squirts out a schedule, and we handle that through Python. The schedule is put into a database, but all of the communication with that database and with that calendar is done through Python. And then there's the telescope operations layer, which is for some reason written in Java, but that's because I think it was started by people over 10 years ago. And so that's just the operating system layer of the telescope, which nobody needs to interact with, except if you want to upgrade it or something, but no user has any interaction with. And so that's how you get an observation done. On the other side, when your observation has been done, the image data is an ORAC and Starlink pipeline thingy. I'm very embarrassed about that. And if you ply Curtis with beer, he will talk to you at great length about why that isn't a lovely two-snake symbol, because we tried for a long time to get that to be Python. It may still in the future be a Python thing. But when the data products are kept track of and then archived, that happens with Python. We have an open access archive, which is in Python, and then the request, the observation request interface, which is the one right at the start of the process, was in Python as well. So there's an awful lot of Python there, which is good, I think, because I can look at any of that code and I can, in principle, understand it, apart from the ORAC, the Gurobi, and the Java. But who really understands those? So we provided a whole load of tools for people to check on what they want to observe, and check on what they've requested to observe, check on their data, and you can do that through, initially we did it through Python. You could import Python. We thought actually it would be much easier if we had it as an API, so we turned that Python into an API, and it just sits on the server and you communicate with it through this API. And if you would like to, you can browse through our observation archive through this API, and the documentation is there. So that would be quite interesting if you have any comments on that. But that's the whole observing process. There are a whole other set of tools that we developed which also were in Python because we couldn't help ourselves. Python is such a lovely language to code in. It's just, I just find it really exciting to be able to, I think I'm not Pi curious, I'm definitely a Pi-vangelist. All sky cameras. We use SBIG 340 all sky cameras, and has anybody ever used an SBIG 340 all sky camera? Okay, well, yes, good. Yeah, well, I know you have, Curtis. SBIG say, here you go, and you have to run Windows in order to communicate with this. So we went, oh, that's a little bit awkward, really, because we want to, use Linux and Python and all that sort of thing. So we had an intern which developed a Python library to communicate with them, and then we further developed it more so it could cope with not only the black and white but the color and produce FITS files and stuff. So if you are still running a Windows box just to communicate with an SBIG 340 camera, please think about using or forking our Pi All Sky. And this is the very first test that we made of this thing running. This is my house, and that's why there's spots all over it. And this is clouds because I live in Wales. 2 minutes. Oh, great, thanks. But Django. Who's heard of Django? Lots of people, great. Well, Django is a web framework which uses Python, but also has nice web templates. And as soon as we realized that you could use Django to do a lot of the web type stuff that we needed to do, it meant that we could throw away PHP, which I slept better after doing that. And I know a lot of you maybe in the room did as well. So now we can use a lot of the back-end Python code in a Django project and have it, instead of having to talk through wrappers and things like that, you can use Django for everything, really, and we do. So I'm just going to show you some screenshots of a variety of our different projects. This is our observing portal. We have 2 slightly different versions, one for professional astronomers and one for like the public and education type users. And it's a Django project. We have our telescope operations interface. You can all have a look at that and see the status of our network at any time, which is, again, another Django project. We have a way to visualize what the scheduler is doing at any time. And here is each telescope in our network. And the green ones are good. The blue ones are weather. And these ones are, well, we won't talk about those ones. They're not good. This is another beautiful thing about Django. You get for free the Django Admin site. So you can just create a Django project, set up all your different models, and then you get this admin site without having to do anything. Well, we're only doing a very minor amount of stuff. And we use this for checking on our data projects and keeping track of what stage in the pipeline everything is. So although the pipeline isn't in Python, checking on each stage is. Our open access archive, we use that. That's another Django project. Because we've just got databases and we've got stuff that we want to do to the data, and we've got web pages. And this is an ideal pairing. And finally, the last thing that I wanted to just put up was we made an education project about exoplanets, but really doing photometry. It's a tool for telling people about exoplanets, but also teaching them how to do photometry. And in the background, you get, well, in the front end, you get shown a JPEG of an image of a patch of sky, and you place apertures over this image. And in the background, it goes off using AstroPyFits and interrogates or does aperture photometry based on the circles that you put down on the FITS data, and then sends it back to the front end. And eventually it builds up a light curve. So you can have a play with that. But that's really using an awful lot of Python. That wouldn't have been possible in the way that we did it so easily without having Python and without having AstroPy. So these are all the different, some of the areas that we use Python in. There are more. So for research, we have portals for our main research areas of supernovae, NEOs, microlensing, exoplanets, and data pipelines, our image archive and data products. For education and outreach, there's Agent Exoplanet and an open access archive. For instruments, testing them in the lab is entirely done with Python. The guy who tests all of our cameras, remember we've got the possibility of 20 telescopes coming up in the next 2 years, and each of them have more than one camera on them. So that's an awful lot of cameras for one person to test. And he uses Python entirely, hooks it up to an oscilloscope and things. For creating images of the data, and for observing with all those different things in all those different ways that I showed. I want to say a big, big, big thank you to the Python developer community, because it would never have been possible to have done this in such a unified way. We've got a homogeneous telescope network. We have a homogeneous software solution. That's incredibly rare. And it wouldn't have been possible if Python wasn't such a beautiful open source community as it is, developing all these amazing tools so that we don't have to do that ourselves. So I'll just finish by putting up my details, and that's me in the TARDIS. Thanks.
Thank you. We have time for one or two quick questions.